sports arena, where yesterday and today they were holding a job fair, a career fair, and that's held pretty much every semester. And if you didn't make it over there today, then if you go to the Student Resource Center, we tried to collect as many pieces of information as we could from employers on current opportunities and stuff like that. And so those will be available in the Student Resource Center. Otherwise, make sure that you go to the next one, the Spring Career Fair instead. A good majority of our students have an internship even after the first year. Many of them will have multiple internships every summer or even going into the year. It is never too early to start. Even if you're not looking for an internship, even if you're not looking for employment, it's never a bad idea to get over there and get some practice, some low-risk practice in talking to employers, handing out your CV or your resume, because they do keep them on file and they do contact you in the future for other opportunities. So keep that in mind. If you didn't know about that, make sure that you're not ignoring our weekly bits and bytes. And make sure that you're not ignoring our weekly retrospective in this particular course, because they were both announced through that. So to get back to what we were talking about on Monday, we finished up with looking at an example and a visualization of how functions actually work. Remember that you have basically what's called a program stack, and this is a visualization of it growing upwards. Where when a program starts out, the program code is loaded up into memory at some point. At the bottom of the stack is where you can visualize it. Then global variables and static content, like if you've got a string or something like that, hello world, then that's loaded up. And then each time a function is called, for example, main, you start out in main, then a new stack frame is created. If main calls another function, say average in the example that we looked at, a new stack frame is created, basically on top, right? If you remember that stack is a LIFO data structure. You push stuff onto the top of the stack, and then you pop it off the top. When these functions start returning because they're done computing and they return a value, then these stack frames are popped off the top, and control is given back to the calling function. When sum is done, then this stack frame is popped off the top. And then what's at the top now? Well, this stack frame, and the regular flow of control resumes in average. Likewise, when average is done, then this stack frame is popped off the top, and control is returned back to main. This is how functions work, because it is a really efficient way of keeping track of breadcrumbs, where you came from. Function A calls B, calls C, calls D. Well, how do you get back to where you came from? You keep track of it through a stack, okay? So what we looked at next is one consequence of this. I wrote a really quick program here to attempt to swap two values. I've got A and B here in the main, and then we print them out. And let me go ahead and walk up to that point, right? A and B are initialized. This is the stack frame for main. Then we walk forward here and we print them out, and of course we see 10 and 20 up here. Okay? Now when we call this function, we jump into the function and a new stack frame is created. Is this A and is this B, is that the same thing as these A and B over here? No. Right? They are parameters to this function. They exist in a different stack frame. They exist in a different scope, so they're completely different variables, even though they have the same name. That's perfectly fine. When we swap them, of course, you see that in action on this stack frame. And if I were to print them out in the function, you would see 20 and 10. But when we return back from back to main, that stack frame is destroyed. That second A and B are now gone. There's no way to access them anymore because the stack frame was destroyed. It was popped off the top, right, even though it's visualized as the bottom here. The original A and B were unchanged. So when we print, then we end up with the same values. Right? This is a consequence known as passing by value. Right? By default, variable values are passed by value to functions in C. Right? That means that when a function is called, copies, all right, here, let me emphasize it, copies of the variables variables values are passed to the function, not the variables themselves. Right? So again, as a consequence, any changes to the variable, the parameter variables inside the function are not seen or realized in the calling function. In this case, we made changes within the swap function, and those that did work. But the original variables, it doesn't know anything about those other variables. Those two stack frames exist completely independent of each other, okay? At least as this is. So consequently, this is called passing by value. We pass values of the variables when they actually get called rather than the variables themselves. And I can drive home the point that this is true by simply just changing this program a little bit. X and Y. Right? I kind of tricked you a little bit by calling them A and B, calling them the same thing. But certainly if I give them different names, it is absolutely clear now that these are completely different variables because they have completely different names. So you have to understand that you can reuse variable names as long as you reuse them in a different scope. You can have multiple index variables, I, J, and K, as long as they're in different functions or as long as they're declared and their scope is limited to the loop itself, right? All right, well, I really want to do this, though. What if I suppose I really want a function to make changes to the original variables, right? Or in other words, swap them, manipulate them, etc. Right? And we'll get into exactly what we mean by, well, what would you actually want to do here? If you're going to swap variables, why write a function to do it? Just go ahead and do it right here. Right? And swapping variables, that's not a very big task or common task anyway. Why are you swapping variables? Well, actually, it's a common task for searching and sorting. If these two things are out of order, you better believe you want to swap them, right? So I really want a function to be able to make changes to my variables. In order to do that, you need to create a function that does not pass by value. Instead, it passes by reference. A function that passes variables by reference instead. Now, the vast majority of programming languages are going to be passed by value. If you get into Java, PHP, Python, JavaScript, C#, most programming languages are going to have a default of having something passed by value. C is one of the few programming languages that allows you to pass by reference explicitly because C has what are called pointers. Right? So to do this, we first need the concept of references of pointers in C. Okay? So I'm going to start a new section here, pointers in C. Okay? There we go. All right. So to understand pointers, first of all, we need to understand memory a little bit more. Every piece of data in a program or a computer or whatever you want to look at or a computer is stored in memory. Right? Well, what is memory? Memory has both an address and contents. Okay? Now, to understand this, I'm going to go ahead and try and switch over here to the .cam because it's much easier to just come on. All right, if I can't do the .cam, come on. Oh, some brilliant genius unplugged it. All right. Instead of they wanted several HDMI plugins apparently. Okay, so I'm going to visualize. Again, it's just a bunch of wires and electricity and gates and stuff like that. But the way that we're going to visualize it is as follows. Memory has an address and contents. The address is not intended to be human readable at all. Right? In fact, it's just a number. That number is generally expressed as a hexadecimal number. So you could have a memory address of, say, 00A B, right? And then somewhere else you have another memory address, 00 CB or something like that, right? And ... Memory addresses are usually contiguous, that you have memory address 1, memory address 2, memory address 3, etc. Generally, the addressing generally doesn't go by byte, but it can. Sometimes it can. Sometimes it goes by word, which is 4 bytes. Sometimes it goes by 8 bytes. And it really is dependent on the operating system, on the actual hardware. It doesn't really matter for understanding this concept. When you create a variable, A, and set it equal to 42, you don't have to worry about the memory address. The program, once you compile it, it just knows, okay, well, I need a memory address to store this variable. It's going to store an integer, and it's going to store 42 at that memory address. It takes care of that stuff for you. In fact, every time you run a program and rerun the program, it loads it up in a different part of memory. So you might get a different memory address each and every single time. You don't have to worry about this cryptic number here. All you have to worry about when you actually write a program is the name of the variable, A. Okay? Later on, you might declare another variable, double pi is equal to 3.14, right? And that might be loaded up somewhere else in memory, 3.14, right? There are contents, which represent 42 or 3.14, and memory has different size. Remember how many bytes are in an integer? Do you remember how many bytes are in an integer? 4 bytes, right? That's 32 bits. 8 bits per byte. A double is going to be, well, as the name implies, it's going to have how many bytes? 8 bytes, right? It's a double precision, so it's going to have 8 bytes over here, generally. Now in C, technically, you know, an integer only has to be at least 2 bytes. There's no guarantee that this is always 8 bytes. But 99% of all systems is going to be like this. A has a reference basically. There's some sort of mechanism in your program that is associating A with this memory address right here. When you set it equal to 42, you are basically filling this memory address, the contents of this memory address, with the value 42. When you set this equal to 3.14, you're setting the contents of this memory address automatically. The program's taking care of it for you, right? But what I want is a pointer, a reference. I can always get 42 by simply printing out A, adding, I can go A++, and then it changes to 43. I can do whatever I want in the program. But what I want to do is I want access to this thing right here. I want access to its memory location. Because if I have access to its memory location, I can do whatever I want here, wherever I want, right? I can just simply jump to this memory location and fill it in with, I don't know, 7 instead, right? And it doesn't matter what function I'm in. It doesn't matter what part of the program I'm in. As long as this memory address, I know that it's 00AB, I can jump to that memory address and do whatever I want with the contents of that memory. That's the basic idea of a pointer. As long as I have something that points to this memory location, I can jump to that memory location and manipulate the contents stored there. Right? That's what a pointer, that's what we're talking about when we're talking about a pointer. All right, there we go. So memory has both an address and contents. You can access contents by using a regular old variable, right? Int A, right? Equals to 42. You can access the address of a memory location using a pointer variable. Oh, sorry. A pointer variable. Okay? So to declare a pointer a variable, you simply use the star operator. Right? And what we mean by star is simply the asterisk. I'm going to go ahead and go into code mode here and show you. Right? Int A is equal to 42. This is just a regular old variable declaration. Right? Well, now how do I declare a pointer? I'll call it pointer to A, because I'm eventually going to make it point to A. That's going to be the name. Is that going to be correct? That's going to be just a regular old integer variable. So if I want to make this a pointer to an integer, then I can go ahead and put a star in front of it. Now this is this declares a pointer variable that can point to a memory location that contains an integer. You can technically make it point to a memory location that stores a double. You can technically do that, but you shouldn't do that. Why? An integer is how many bytes again? 4. And a double was how many bytes? 8. So if you force an integer pointer to point to a double location, you're ignoring half of that memory. Likewise, if you force a double pointer to point to an integer location, now you are not accessing 4 bytes of memory, you're essentially accessing 8 bytes of memory. And you'd better hope that that works. Right? We'll see the consequence of when it doesn't work. All right? At this point, pointer to A does not necessarily point to anything. Right? Remember, if I just declare an integer A and I don't set it equal to 42 immediately, what value does A store? Who knows? It could be 0. It could be dead beef. At this point, pointer to A does not necessarily point to anything. It could point to an invalid memory location, a memory location that doesn't even exist. It could point to a memory location that doesn't belong to you. Right? Not all the memory belongs to your program. The operating system, when it creates a program, it gives you a stack. And it also gives you a heap, but we'll talk about that later. So when it gives you that stack and you try to access memory that doesn't belong to you, the operating system is going to sit there and say, that memory doesn't belong to you, I'm going to kill the program. Right? Did anybody remember when they started out and started doing scanf and stuff like that? And if you screwed it up and you forgot your ampersand, what kind of an error message did you get when your program died? Remember? Or maybe everybody did it perfectly. It results in a memory dump. The message that you get typically, though, is segmentation fault. What is a segmentation fault? Well, memory is organized into segments. If your program is in this segment over here, and you're trying to access memory over here in a different segment that doesn't belong to you, then it's a segmentation fault. You're trying to access memory that doesn't belong to you, and the operating system, a good operating system, will be able to detect that and say, no, you can't do that, I'm going to kill the program. And it results in a segmentation fault. Imagine if you were able to do that. Imagine you could write a program that could just arbitrarily access any piece of memory that you want in the computer. What could you potentially do with that? How, though? You could start stealing stuff from the operating system, and you could crash your own computer. But think more nefariously. Run on CSE. Do you think that there are programs on there that hold sensitive information, like passwords, encryption keys? Everything is held in memory, including sensitive stuff. If you can write a program that can arbitrarily access other programs' memory, then you could write a program potentially that is scanning for SSL keys, secure socket layer keys, on the CSE server, and now you've broken all encryption going to the CSE server. Not that big of a deal for the CSE server, although the sysadmins would say otherwise. But imagine that you could do this for an arbitrary computer. This is exactly what happened with the Heartbleed bug several years ago. Do you remember the Heartbleed bug? All right, it was a bug in OpenSSL, which is a security library that was used by something like 30 or 40% of all the web servers in the world. And you could send a malformed request to one of these servers that was affected, and basically you would get back a random location of their memory, their memory contents. Well, it doesn't really matter if you get back an image or something unsecure, but if you keep doing this over and over and over again, the likelihood that you're eventually going to get some encryption keys out of it is big, right? especially if you're allowed to do it over and over and over again. You just do it until you actually get those SSL keys. And once you've got those SSL keys, then you can sit in the middle of any communication going to that web server, and you can listen to everything, right? So it is a huge security issue if a operating system does allow you to arbitrarily access this memory, right? Now, in that particular case, it wasn't an operating system flaw. It was an actual flaw in the library itself that didn't have a buffer overflow check, and so you sent sent just the right commands to the web server, and instead of saying, okay, well, you can only have this much memory, then you could say, I want more memory than just that. Well, then the likelihood that there's something stored in this other part of the memory that belongs to the program, you can just grab that stuff. You could have just grabbed that stuff. It was a huge flaw. I don't know how many years it was alive, but it affected over 40% of all web servers or something like that. And the fix was not just to fix the bug. The fix was to go back and invalidate every single key and redo every single key for every single server that was out there, which was a huge ordeal. Right? So you have to think about security when you are allowed such low-level access. With great responsibility, or with great power comes great responsibility, right? You want to make sure that you're only accessing the memory that belongs to you, and you hope that the operating system is enforcing that and killing your program with a segmentation fault when you do violate that stuff. Okay. So what does it point to? I have no idea. Right? It is best practice to initialize a pointer to a valid memory location, or, failing that, to null. So, what is null? Null is yet another concept of nothing. We've now got several concepts of nothing. 0 is nothing, all right? And we'll have several more after this as well. A function that does not return anything returns what? What's its return type when you write a function that doesn't return anything? Remember? Void, right? So void is one concept of nothing. And here we have yet another concept of nothing, null. It's usually, each one of these concepts of nothing is used in a different context of nothing. Numerically is 0, when you a return type, void, and a memory location that points to nothing, we use the keyword null. It is all caps, N-U-L-L. It's defined in the standard library, and you will see plenty of people that say that it's equivalent to 0, and for all intents and purposes it is, except that it doesn't necessarily get compiled to 0, so don't use 0, use null. All right? You might be tempted to instead use 0 to represent this, but don't do that, use null. Okay? So here's the example. Right? Instead of declaring it up here like this, what I should have done is, I should have immediately set it equal to null, unless I wanted to know what exactly what I want it to point to. Okay, so you can set it equal to null, and then later on in your program, if you want to check for null, you can do an equals to null. So if pointer to a is equal to null, then I don't know, print something, printf invalid pointer, right, or something like that. Okay. So you can set it equal to the null. You can test whether or not this pointer is null. Right? So how do you make a pointer point to a valid memory location? Remember, because you have two options here. You can make it point to a valid memory location, or failing that, if you don't know what you want it to point to immediately, you can just initialize it to null. Either way, it's best practice to do one or the other. Right? Well, first of all, we need to be able to get the memory address of a variable. Right? A variable's name is its content. Right? That if I go int a is equal to 42, setting a equal to 42, I'm directly accessing the content. I'm putting 42 into the memory contents. But if I've got a regular old variable and I want to get the memory location instead, right, then I need to use yet another symbol, right, to get a variable's memory location. Use the referencing operator, which is going to be, looks kind of familiar because you have used it before, and when we started using it, I told you, don't worry about it yet. Well, now you have to worry about it. The ampersand. Where did we use that before? With scanf. I told you if you don't have it with scanf, it's going to lead to a segmentation fault. And now we're starting to understand why. Because with scanf, I was not passing by value. I was passing by reference. I was passing a memory location. And we'll dive deeper into that here in a moment. Right? To get a variable in this memory location, we need to use the referencing operator. And here's our example. All right? I'm going to make that variable point to A. So pointer to A is equal to, now this is incorrect. Right? The thing on the left-hand side, as I declared it up here, that is a pointer. That is a memory location. That is a reference. The thing on the left-hand side is a reference. The thing on the right-hand side, that's a regular old variable. So these two things don't match. I need to make the thing on the right-hand side into a memory location. And the way that I do that is by simply placing an ampersand in front of it. Instead of the contents, A is just the contents, I'm putting ampersand A, which is now the memory location. Right? So in the example that we did over here is 00AB or something like that. Okay? And this makes pointer to A point to the variable A, right? By listing out its memory location. Okay? So what I want to do now is I want to show you how this kind of works. Let me open up memory.c. Okay. Include stdlib.h. Include stdio.h. Int main, int argc, char argv. Hey! Star. I kind of know what those are now. What is that? Star, well, just one of them. argv. What's that? It's a pointer to a character. So star, what if there are two of them? What do you think? A pointer to a character. Why would you want two pointers? You've got a pointer to a, you can go as far as you want, by the way. A pointer to a pointer to a pointer to a pointer. That's how we do arrays. And that's how two of them mean it's a two-dimensional array. An array with rows and an array with columns. Right? And that's why this is basically an array of strings, because a string is nothing but more than an array of characters. But we'll eventually get to that, so don't worry. Right? Don't worry about star yet. Again, let me go ahead and create this variable, 42. And let me go ahead and create a pointer variable. And I won't initialize it. Let me print it out and see what it looks like. So A is going to have a value %d. Pointer to A is equal to %something. Right? So A and pointer to A. So I need a placeholder here. So %d is it's integers because it's kind of digit. %f is for floating point numbers. %c makes more sense because it's for a single character. What do you think the placeholder might be for a pointer variable? A pointer variable. P. Right? So you can print out the value of a pointer here. Right? And this one actually makes sense. Right? So A is 42, and a pointer here is uninitialized. It's going to be 0. And that's just the operating system, that's the compiler, saving me from myself. It's automatically assigning to null for me. Let me go ahead and show you that there's no difference. That there's no difference here. Run it again. All right, it's pointing to null. Okay. So what do you think happens if I try to print out the value that's stored at that memory location? Does the null memory location exist, do you think? Does nothing exist? No. So if I tried to print it, I've got a pointer that points to nothing, right? I'm not even going to point it to any particular place. It just points out there in the ether. If I try to access that memory location that doesn't exist and try to print it out, with the value stored there, the value stored at that location is %d. The way that I can do that, here's a preview. I'm going to dereference that pointer. Right? Don't worry about that yet. We'll get to that in the notes. GCC. Let me go ahead and try. What do you think is going to happen if I try to access a memory location that doesn't exist? Segmentation fault. Right? What do you think if I try to access a memory location that might exist, 1, 2, 3, 4, but that doesn't belong to me? Right? That probably belongs to the operating system. Right? In fact, it's giving me a warning about it. That's just a warning. Don't worry, you can still do it. C is one of those languages that if you want to shoot yourself in the foot, it's going to ask you what caliber. Right? It's not going to say, are you sure you want to do this? Right? It's just going to say, yeah, go ahead and do that. Right? So what happens if I try to access a memory location that doesn't belong to me? What happened when you forgot an ampersand with scanf? Right? Segmentation fault. So now let me go ahead and change it so that I'm actually pointing to A. Where is A stored and what is stored in it? When I do this, there's the memory location of A. Instead of, it's still some mysterious number. I don't know what that means. It's just some hexadecimal number. It's stored somewhere on my computer, and that's where it's stored. It has a value of 42, and now that that pointer variable is pointing to that variable, I can actually access its contents through the pointer and get 42 out of this. If I ran this again, would you predict that it's going to give me the exact same output? Think about what's happening in a computer. Hundreds of programs are being run every nanosecond, right? So if I load up a program in memory somewhere, some location in memory, it runs, it ends, and I run it again, how likely is it that it's going to be loaded up in exactly the same memory location? Probably not likely at all. Right? And you see that it was loaded up in a different memory location. Right? It is, in fact, different. 655, this was C6D, right? It's somewhat close together, but that's just because I'm in user land right now. If I run it again, and again, and again, and again, they're going to be all different. Right? In fact, if I told the other class that if I ever do get the same, I'm going to go out and buy a lottery ticket because that means that I got extremely lucky, and so maybe I'll get lucky on the lottery ticket. Then we started talking about the spread with Ohio State, and we can talk about that afterwards if you want to. All right. All right. Don't gamble though. All right. Okay. So I'm making something point to a memory location. If you have a regular variable, to get its memory address, you use what I just said, the referencing operator. Right? And again, that is going to be the ampersand. If you want to go in the opposite direction, if you have a pointer variable to access its contents, right? That is, change it into a regular old variable, use the, well, what's the opposite of referencing it? I'm dereferencing it. Use the dereferencing operator. Right? Now, just as plus, what's the inverse operation? Minus. Multiplication, the inverse operation is going to be division, right? So how do I reverse this? Unfortunately, they didn't use yet another symbol. They reused another symbol, so star, right? And that's what I was doing over here in this example. I'll open it up back in Emacs again. I was putting this, this was a pointer variable. To change it into a regular old variable so you can get the contents and print them out, I put a star in front of it, just like when I declared it. That's the dereferencing operator. So these are opposites of each other. If you have a regular old variable, then you can change it into a pointer by using ampersand. If you have a pointer variable, you can change it back into a regular old variable using the star. Right? Is there a question? Yeah?
Yeah, I mean, you told us not to worry about the double star, but if you dereference a double star, does it dereference the whole pointer?
Dereference it once, then put it in parentheses, dereference it again, and you get a single character out of it. Yeah.
Well,
you can.
You don't dereference twice,
You can, and we will eventually when we've got when we have need to do so. But there are much better ways of doing it. We're going to be talking about arrays, and we're going to be talking about the two-dimensional arrays. And instead of dereferencing it, what we're going to the way that we're going to do it is we're going to index things. using the square brackets rather than directly dereferencing. Okay. All right. Well, we have enough now that we can actually revisit the swapping demo. Visit swapping demo. Okay. So what I want to do is I want to come back over here and I want to rewrite this program. Okay. I want to write it so that I'm not passing a regular old variable here. Instead, I'm going to be passing a pointer variable. So int x, that's a regular old variable. How do I make that into a pointer integer pointer variable instead? Put a star there. Likewise, this one over here. Right? Now, x is no longer a regular old variable, so I can't take the contents of x and place it into temp. What do I need to do? I've got a pointer variable now. How do I change it into a regular old variable? Dereference it. Right? Likewise with y, and again x, and y again. Right? I'm taking all of these pointer variables, x and y, I'm dereferencing them so that I can grab the contents out of x, I can grab the contents out of y, and I can put them back, or I can swap them. Okay? But I'm doing it by reference, meaning that I'm jumping to the memory location where these things are located, and I'm directly accessing the contents. Now, let's go back over here to the main. A and B are regular old variables. Does swap now take regular old variables? Nope. Swap now takes what? Pointer variables. So if I have a regular old variable, how do I change it into a pointer variable? Put an ampersand in front of it. Put an ampersand in front of it. Right? And now let's see what this looks like. Right? I like this visualization because it should also visualize what we mean by a pointer. It's not going to be it's going to be a stack frame that's going to be it's going to be a memory location that ends up pointing back to the original variables. So let me go forward here. I've got A and I've got B. Print them out. Yeah, 10 and 20. Go forward. Here's my new swaps stack frame, right? X and Y are now pointers, and you can see that there's a word there now, pointer, right? So I'm going to go ahead and go forward to the first line here, and you see what that looks like? They're not different variables now. They are references back to the original variables, and I wish it would. I wish you could move this around. You can't, but you see that Y points back to B, and X points back to A. Right? So when I go forward and I access the variable in, I dereference X, meaning that I start here at X, and I dereference it. I'm jumping over to A to get 10, so that I can put that into the temp variable. Right? Then what I'm going to do is I'm going to jump to Y. Right? On the right-hand side of line 3 there, I'm going to jump to Y to get that value, 20. That's what dereferencing does. Then I'm going to jump to X and put 20 back in there. And so I see 20 now. Likewise, when I'm going to jump to Y and put in the variable temp here, 10, and now those are the original variables. These original variables are in the main stack frame over here. They've now been swapped. So if I go forward here and go back to the main, only the pointer variables were destroyed. We no longer have copies A, B, or A, B, and X, Y. Right? When I print this out, now they've been successfully swapped. Because I was passing them by reference. I was giving swap the memory location of these things, and consequently it can jump to those memory locations and do whatever it wants with it, including swap them out, change the contents, access the contents, etc. Yeah? Are pointers always integers? No, you can have pointers to doubles. Right? Oh, it depends on the variable. Exactly. You can have a pointer variable point to any other type of variable. Right? So for example, I could have a pointer variable to doubles, right? Int A is equal to 42, double B is equal to 3.5, and I can have int star ptr to A. I will truncate, and I can make it point to A. I can create a double pointer, ptr to B, and I can make it point to B using very similar syntax. You can have a pointer to a string. You can have a pointer to a string. You can have a pointer to a pointer to a pointer to a pointer. You can have even what's called a void pointer. All right, so it's a nothing pointer, and we'll talk about that much later. Okay, don't worry about that yet. Not only that, but towards the end of the semester, you can have a pointer that points to a function itself. They're called function pointers. Why would you want to do that? Well, we'll get to those reasons eventually. Okay, a pointer can point to anything because everything is stored in a memory location, and a pointer is nothing more than a memory location. So anything that's stored in a computer, you can have a pointer point to it. Okay? All right. Let's see what else. That's good. All right. So pitfalls. Or pitfalls. There we go. You cannot arbitrarily assign values to a pointer, right? For example, you can't do what we did before. Let's say that we've got int star ptr to a, right? This is going to be uninitialized. Could point to garbage, right? Or anything. Right? You could make it point to something else. You could say, let's see, this points to an invalid memory location, or a memory location that does not belong to us. Right? If I just go ptr to a is equal to 1, 2, 3, 4. Right? Well, that might be a memory location. It might exist, but it probably doesn't belong to us because it's just some rando memory location. Okay? So you can also make the mistake of making a pointer point to something that doesn't exist. For example, int a, let me go ahead and restore that. Int a is equal to 42. The following is also wrong. If I go with ptr to a is equal to a, why is that wrong? Again, what is that thing on the left-hand side there on line 194? It's a memory location. What is the thing on the right-hand side? It's a regular old variable. They don't match. What is ptr to a actually pointing to now? Memory location 42, right? Which again is kind of like this over here, just assigning it to some random memory location that probably doesn't belong to you, right? All of the above will likely, in fact, hopefully, result in a segmentation fault. Right? And even if it doesn't result in a seg fault for short, you might be corrupting your own memory. Right? So let's see. Let me go ahead and go back to this demo over here. Actually, no, let's go to the command line demo over here. And let me go ahead and change the pointer to a. Right? What I'm going to do is it's pointing to some memory location. What I'm going to do is I'm going to make it point to 1 byte further, or something, whatever addressing system it's using. The way that I'm going to do that is by simply adding 1 to it. I could have gone plus plus if you really wanted to. And let me go ahead and cut and paste this up here. Okay, I don't have enough room, so I'm going to have to fix it now. Oops. Pointer, there we go. And let me go ahead and compile that and see what happens. So originally it was pointing to memory location, whatever. The value stored at that location is 42. By incrementing it by 1, I'm taking it, and it's not only pointing here anymore, it's pointing over here. Okay? And when I do that, it's what value is it interpreting that as? Negative 445, blah, 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 blah. Right? Is that a valid value that we used in that very, very simple program? No. It's just interpreting it as a number. There are some bytes in there, there are some bits in there, and who knows what the hell they are. But it's trying to access them, and it's trying to manipulate them. So let's go ahead and change it. Right? So I'm going to dereference pointer to a, and I'm going to assign it a value. Instead of 42, give me your favorite number. 6? Okay, there we go. And let's do it again. Let's try to print it out again. Right. Oops, sorry. I meant to run it. There we go. Oh, darn it. Oh, whoa, did we get lucky here? Oh, we got lucky. All right. So what I need to do is, after I've changed it, I will go ahead and take it down a notch here, pointer to A, minus, minus. Now I'm going to make it point to the original. Actually, no, sorry. What's stored at A now? Was it 42? Oh, wow, we got lucky. We got lucky, and we went past whatever A was whatever was being stored at A by just going by plus plus. Probably it's addressing it by word here. Okay, we got lucky. Let me go ahead and instead of going by 1, let me go with 500 bytes later, or 500 addressable bytes later. And let's see what happens now. I'm going completely somewhere else. Now it's a segmentation fault. I went out of my own segment. 500 bytes apparently was beyond where it should be. Let me try to go the other direction. Let me try to go lower in the stack and start manipulating stuff down there. Let's see what happens. Probably another segmentation. Oh, no segmentation fault. No segmentation fault here. But if I continued, and if I had other stuff, I would eventually get a memory corruption error. Hopefully I would get a memory corruption error at some point, or a segmentation fault, a core dump, a memory fault, or something like that. Basically, I've corrupted my own memory in this program. It's just not apparent that I've done that. And so eventually when you get to more complex programs, you could be corrupting your own memory and you don't even know it until it pops up that then it all crashes or gives you unexpected results or undefined behavior. Yeah?
Looks like it failed to edit the value of the pointer.
Let's see, where? This?
On that middle line, yeah.
Yep. The value stored at that location. Actually, it went down 500 bytes, and we just got lucky that a bunch of zeros were stored there. Right? That's my guess. Right?
The memory address is identical to what it was just at.
This is after we set it to 6, though.
Oh.
Right. So we jumped down 500 bytes. It was all zeros. We set it to 6, and then we printed it out again. Right? All right. So I'll go ahead and preserve that in the notes later on. Right? So even if it doesn't result in a segmentation fault, you could still be corrupting your own memory. And it's luck of the draw, right? I wasn't able to force it to corrupt my own memory and give me something meaningful or any visual indication that was happening, right? Okay. Let's see. So, review or summary. Now you can recall that scanf, whatever percent LF, percent, I think we used B for the floating point number, right? Used an ampersand. Now, do you understand why? Why is it the case that it was passing not by value, but by reference here? Right? Scanf is passing a variable by reference. Why? Think about it if it wasn't by reference. Get rid of that percent sign there, or get rid of that ampersand there. You're scanf, and I'm the main. I want to call you, and I want to say read from the command line and give me the result. But scanf doesn't return a result like square root or sine or something like that. Instead, what I do is I need to tell you, now you're scanf again, I need to tell you where to store whatever you read from the standard input. In other words, I've got my variable here, A, and I want you to store that result in A. I want to pass you this variable. If I just passed you the variable A, you wouldn't be able to make any changes to the original variable, as we saw with swap. So instead of passing you A, I pass you the memory location of A. With the memory location, you can go ahead and go to the standard input, read in whatever integer you want, and then you can jump to that memory location and you can put the results there. I like to call it giving you a bucket. I'm not giving you a value. I'm not giving you 10 or 42 or 6 or whatever, right? I'm giving you a bucket to put things into. You can put the things into the bucket, and we both have access. We've both each got a hand on the bucket, and we know about the bucket and where the bucket is. And once you put something into the bucket, I can take something out of the bucket. It only works if we have a bucket that we share. If I'm simply just copying a value and giving you 10 instead of a bucket that can hold 10, then there's nothing that we can communicate back and forth, right? So functions that take pointer variables can make changes to the original variable if needed. Right? We've got the referencing operator, where you can change a regular variable into a pointer variable. This is, again, the star operator, or the star. And you have the dereferencing operator. You can take a pointer variable into a regular variable. Right? And again, the one here is, what is it again? If it's not star, then it is ampersand. Right? Okay. Well, again, this seems maybe useful. It's definitely useful with scanf. But the examples that I've shown you so far is only swapping, right? And again, swapping, who cares? You can just swap, and why are you swapping to begin with, right? But it also allows you to basically free up the return value. Pointers allow you to free up the return value, right? Instead of returning a result, you can set the values of a pointer or multiple pointers. Right? In other words, as a consequence of this, you can write functions that return, and I put it into quotation marks here because it's not actually returning anything. You can return multiple values. Right? You can't do this in general with functions. Right? Instead, you can only return at most one value. Return a double with square root. Return an integer with abs or something like that. Right? There's a question over there?
Yeah.
Go ahead.
Previously, you said that the referencing operator.
Oh, did I screw up? Ah, darn it. Damn it. So dereferencing operator, pointer variable into a regular variable. Sorry. There we go. And then referencing operator. Thank you. Right? Sorry for screwing that up. Right? It's hard enough to remember the difference between the two. It doesn't matter once you write a program and you see, oh, segmentation fault. Oh, maybe I need to switch those around. Right? Sorry. And then there was another question, or was that it? Okay. All right. Thank you for correcting that. So what do I mean by returning multiple values? So let's go ahead and go back to this visualization over here. And instead of doing swap, let's do, we've got plenty of time here. Let's go ahead and do the quadratic roots program that we kind of worked on in the very beginning, right? So if I've got int a, b, and c, say 30, right? I want to compute the roots of this thing. Remember, the roots are going to be what's the formula? It's going to be negative b plus minus square root of b squared minus 4ac all over 2a. Is that correct? All right, great. So what would you have to do if you did this using functions? All right, I want to create root 1, or let's make them doubles, root 1 and root 2. Right? Well, if I just did this with straight up regular old functions, I could write one of them. I could say double root 1, first root, and I'll take int a, int b, and int c. You can change those to doubles if you want to. And I would have to make a choice. Do you want to compute the plus or the minus root? Let's go ahead and do the first one. So return negative b plus square root of, b squared minus 4ac. There we go. All over 2a. And put this into parentheses 2. Great. Right. Can I return both? Can I return plus minus? Oh, that's not even correct syntax. Can I return that one and then also return the negative one? No, there's only one return statement. There is only one return value that you can do with any of this stuff. Okay? So what do I have to do if I want to be able to compute both roots? I need a function called first root. I need a function called the second root. And I'll do with the first root is going to be the plus, and then the second root is going to be the minus. Let's make sure that this works before we start making changes. Root 1 is equal to first root of a, b, and c. And root 2 is equal to second root of a, b, and c. And then I'll print them out. Roots are %f, and the line root 1 and root 2. There we go. Let's, anybody see any problems? All right, give me a, I think, let's go ahead and make this small and this small. And I have no idea what the values are going to be. Oops, what did I forget? Include, might as well do them all. Include the standard input-output library, include the math library. There we go. And instead of doing it here, let me go ahead and emacs roots.c. And let me do it over here from the command line. All right, hey, great, it compiled. I didn't have any problems there. Does anybody know what the roots of those things are going to be? All right. It looks like at least they're real, right? At least they're real roots, okay? But it forced me to have two functions. How could I do this with just one function? Double compute roots. Right? And it would take also A, B, and C at least. Right? Well, I don't want to use the return value here. The return value is what's killing me. I have to have two functions because I want you compute the roots and give me two values back. Right? You can't do that because you can only return one value. But if I gave you two buckets to fill, then you don't have to return a value at all. If I gave you two pointer variables, you could go ahead and go to those locations in memory, access those memory locations, and then fill those buckets for me. And we would share those buckets, and I could actually see that. Right? So I'm going to go ahead and add two pass by reference pointers here, root 1 and double root 2. Okay? I'm running out of room, but that's okay. Come on, there we go. All right, let's compute the first root. Well, it's this. I don't return it, though. Instead, I set root 1 equal to this thing. Now, is that correct? The thing on the left-hand side is a what again? It's a pointer. The thing on the right-hand side, is that a pointer or memory location? No, it's a double. So how do I make these things match? Careful. Yeah, I might have screwed you up on that by marking the notes wrong. It's going to be the dereferencing operator. I've got a pointer variable here. I need to make it into a regular old variable so that I can assign it a value. Right? And once I've done that, well, what do I return? Nothing. Right? Because I want to return two values, I simply do it by reference instead of returning a single value. Right? All right, how do I actually call it then? Let's get rid of these two things. I'll go ahead and do that and that. Now, I want to compute roots, right, of A, B, and C. How do I pass in root 1 and how do I pass in root 2? Root 1 is a regular old variable, right? But this is expecting a regular old variable? Nope. It's expecting a pointer. So how do I change a regular old variable into a pointer? Ampersand on both of these things. Right? All right, and now I'll go ahead and cut and paste this and work from the command line here. Here, remove roots, Emacs roots, cut, paste, GCC, run it again, and I get the exact same answer as before, right? No. Oops. Oh, what did I? What, oh, thank you. So plus, minus. Oh, yeah, there we go. GCC, run it again. And there, now I get the same exact roots as before. Yeah, and the same order too. Right? So already we have a use case for pointers. If you need a function that needs to return multiple values, then you can give it multiple pointer variables. You can give it multiple buckets to fill. Right? You can also make an observation here that, well, compute roots. Now I'm not returning any value here. But some things could go wrong. For example, let me go ahead and go back to the command line here. And let's see, let's make B small and A and C large. So what's going to happen now? Nans. Okay. What's going to happen if A is, instead of 30, it's 0? It'll divide by 0, so nan and negative inf, right? So in other words, there are some things that I could give this compute roots here that would screw up the answers. Another thing that I could screw up, it would be what? If I didn't give it a valid pointer. What if I gave it null? Right? It tries to dereference this null pointer over here. What's going to happen? Let's find out. Segmentation fault. Right? In other words, there are inputs to this compute roots that we may want to handle differently, just like in all of your programs up to this point. If in your retirement program you exceeded the $18,000 annual limit, right, then you stop the program and you output a message. But now that we're getting into writing our own functions, we need to start doing error handling at the function level. In other words, if you give bad inputs to a program, it stops and outputs an error message to the user. If you give bad inputs to a function, the function will not execute. It's called defensive programming. You look before you leap. If you're about to do something illegal, like divide by 0, or have imaginary roots, or you've got a memory location that you're about to dereference, then you don't do it. You check for these things first, and if you're going to do something illegal, you say, no, I can't do that. I'll return from the function. But instead of telling, failing silently with a void, what we're going to do is we're going to return an integer. That integer is going to end up being an error code. Okay. So that's what the next module is all going to be about. But before we leave, or we can end early today. Before we leave, I want to just draw your attention to, let's see, Bret Hart. Null pointer dereference. All right, it's a video that I always share. Yeah, here we go. Okay, yeah, only 10 seconds here. I don't know if they've got audio on this or not, but hopefully. Oh no. Program audio. There we go. No. Well, yeah, but it's only playing on my speakers instead of the speakers out here. And I've unmuted it, so let's try it. Maybe it just needed to wake up. Okay. So then I will hold it up and see if we get some feedback here too. All right. So you saw me what happened when I passed in null to this and it tried to dereference it, right? So anytime you get a segmentation fault, that's what's happening. So always remember Bret Hart's video here. By the way, Bret Hart was a wrestler in the 80s. He's still alive.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
All right. So anytime you get a segmentation fault, just remember Bret Hart.